In this video, I want to go through a quick revision on how to do shear and bending moment diagrams. The assumption is that you've already learned this before, but you might need a quick refresher. And so we're going to jump into it with this example here where I have a simply supported beam with a uniformly distributed load. And what I need to do is draw the shear force and bending moment diagram for this beam. So if we're going to do this first, let's put just some quick labels on here. Let's call this reaction reaction A, this reaction B. And the first thing that we need to do anytime that we have a statics problem is really to draw the free body diagram and define the reaction. So we'll start with that. So we'll do find the reactions. And as I said, one of the first things we need to do is draw the free body diagram. So I always like to remember this little acronym anytime I get into trouble with a statics problem. Draw the darn free body diagram. It will always help illuminate the problem for you. So let's do that. So for the free body diagram for here, we have our beam. We have our reactions at A. So we've got RAX and RAY. And we have our reaction at B, RBY, and we have our load W and our distance L. So now that we've got a free body diagram, let's use statics and equilibrium and solve for these reactions. So we'll run through this quite quickly. So if we do the sum of the forces in the x direction, that has to equal 0. So we can see the only thing we have here is RAX, so RAX equals 0. I'll take the moments about A now to try to find this reaction at B. So sum of the moments at A equals 0. So I have, and I'm using counterclockwise as positive here. So I have the force of negative W times L, which is this distributed load multiplied by the distance which it acts over. And then the resultant force for this will act, because it's a uniform load, it will act at L over 2. So it has a distance way of L over 2 plus the reaction RBY times the distance L, and all of that has to equal 0. So let's do some algebra real quick. We've got RBY times L equals WL squared over 2. So RBY equals WL over 2. And then finally, let's sum the forces in the y. We have RAY plus RBY minus W times L equals 0. We get RBY is WL over 2. So if we solve all of that, we have WL minus WL over 2. That gives us negative WL over 2. Put that to the other side. We get RAY equals WL over 2. So always we want to, whenever we do a problem like this, we want to take a moment and do a does this make sense check. And it should, so if we sort of redraw, the free body diagram of the beam, And we'll do our forces in red here, just to make them show up a little bit more vividly in the video. So we will have W as this uniformly distributed load. And we have the force WL over 2 at each of the reactions and over this distance L. So as I said, let me bring that up so you can see it. As I said, the thing we always want to do is double check, does this make sense? Does this fit with what our intuition would be? And it does. You know, we have a symmetric system. We would imagine that the reactions would be the same. The other thing that we should always do when we're doing a statics problem is do a statics check, just to make sure that the reactions which we have are correct. And so by a statics check, we'll do it over here on the right-hand side. Statics check. So all we're going to do with a statics check is we're going to sum the moments about a point which we haven't done already. So it could be out here, anywhere, it doesn't really matter. I'm going to sum moments about B because I summed them about A previously. And what I want to see is that everything is in equilibrium. So essentially that 0 equals 0. So for our statics check, we'll do the sum of the moments about B. That needs to equal 0. So what do we have? We have the reaction at A, which we know is WL over 2. So we'll do, and that is going in the clockwise fashion. So we have minus WL over 2 times L plus this force W times L, W times L, and the resultant of that is acting at L over 2. And it's going to be L over 2, and that needs to equal 0, and so we get minus WL squared over 2 plus WL squared over 2 equals 0. 0 equals 0. Good. So our statics check is done. It's done correctly. So now we can now move on to drawing the shear and bending moment diagram. And so what we're going to do is we're going to start basically by taking free body diagrams along this beam. And so we'd sort of think of this as like the brute force method. It will always work. But it is, maybe just a little bit slow. So, in order to find, so that's what we're going to do next. We're going to go, to find the shear and bending moment. At any location, take a free body diagram, cut. So again, let's draw that darn free body diagram. Will always get us where we need to be. And so that's what we're going to do. And like I said, there are other ways to draw the shear and bending moment diagrams, which we will look at here shortly. But we know that this method will work, and it will always work. So if you're ever lost, you can always come back to just taking some free body diagrams and taking some cuts. So that's our load, WL over 2. So I want to know, to draw the shear and bending moment diagrams, essentially all it is I'm going to plot, well, what is the shear force at all points along this beam, and what is the bending moment at all points along this beam. And so because we have a uniformly distributed load, the beam doesn't change, loading or anything there, we've got a uniform, so we can do this all with one cut and one set of equations. So what I'm going to do is I'm going to come in a distance of x, and I'm going to take a free body diagram of the beam at that location. So if we come down here to free body diagram at x, we'll just draw our beam in here. So this is our little beam. That beam has, some uniformly distributed load. In fact, I'm going to take the cut bit and I'm just going to make that a little bit jagged just to show that for us. And so that uniform load is W. It has a reaction WL over 2. And as I said, it's some distance x long. And inside here, so anytime we take a cut, we're going to expose the internal forces in a structure. And so it will have a little internal shear force, and I'm just going to draw that pointing down for now, and we'll have an internal moment, M. So we've got the shear force V. And so, but, because the element is in static equilibrium, we can still go back to summing of the forces, summing of the moments, to determine what all of these are and to make sure that they are in equilibrium. So that's what we're going to do. And then we can use that, and that will generate an equation, or two equations actually, one for the moment, one for the shear force, by which we can then use that to plot up our bending moment diagram. So we have two equations. So we've got two unknowns. We only need two equations to solve them. So we're going to start with the sum of the moment at the cut face. So just right here. And we're doing that because then the shear force is zero distance away, and so it does not generate a moment. So it's a nice way for us to solve for that moment directly. So we have the moment, M, going this way, plus the shear force, which is acting at a distance 0 away, so that goes away, plus W times X, which is that force, and that is acting at a distance x over 2 away, and then minus WL over 2 times x, and all of that equals 0. So let's do a little bit of rearranging here, and what we find is we have, m plus wx squared over 2 minus WL times x over 2 equals 0. And so m equals minus wx squared over 2 plus WLX over 2. Excellent. So now we have an equation for our bending moment diagram. And we have this equation because we have this nice continuous load. This equation we can use this to plot our bending moment diagram for any location where x is between 0 and L. Excellent. So let's do a similar thing for the shear force. So we will go sum of the forces in the y equals 0. So I have WL over 2 minus W times X minus V equals 0. Rearranging that, I get V equals WL over 2 minus W sub X times X. And that's it simply there. We now have both equations that we need in order to plot the shear and bending moment diagrams. But before we get into plotting those, I just want to have a quick note on sign convention. So we'll do a quick note on sign convention. And for shear, and the reason we're going to have this discussion on sign convention is so that when we're plotting these things, we're plotting them consistently, and we're all doing the same thing, so that we should hopefully avoid confusion on, I know some disciplines, so particularly mechanical engineering, will plot bending moments differently than we do as structural engineers. And so this should hopefully at least make everything consistent within this course. So for shear, if I draw a little block, this block, I will say it's got positive shear if the shear forces make this block want to spin clockwise. So we'll write that down. So if the internal shear force put spins in quotations, spins the element clockwise, we're going to call that positive shear. And so the nice thing about thinking about this in terms of which way do these shear forces want to spin everything is that, you know, we could be working with a beam, which is horizontal, we could be working with a column, which is vertical, or an element at any angle. And then it's that internal shear force, you know, whether it's wanting to spin this thing clockwise or counterclockwise will determine whether it's positive or negative. Instead of having to remember a rule of like up on the left, down on the right, we can just go back to how it's spinning this little element. And then for the moment diagram, if we have our little block here, what we're going to do, and this is where we're going to differ from maybe how you've learned shear and bending moment diagrams in the past, is that for structural engineering, we always plot the bending moment diagram on the tension side, which means we will plot it on the side where there is the tail on the bending moment arrows. So as the first thing to know is that we will plot on the tension side of the element, and that's going to be, you know, we can say where the tail is. The is on the moment arrow. And then in terms of, well, what is a positive moment, what is a negative moment? A positive moment is going to be compression on the top. And so that would be a beam, what we call happy beams. It's a beam which is smiling, where if we're bending the beam like this, it puts the top, it squishes the top, and it extends, and it pulls the bottom. So if I have my little foam beam here, my foam beam, if I put it like this, the top is getting compressed, the bottom is getting stretched, and so this would be a positive moment. Similarly, this would be a negative moment where it's getting pulled down. And we'll write that one down too, just for completeness. So a negative equals compression on the bottom. So we've got our, shall we say, frowning beams. A little bit sad there, and so that means that top is in tension and the bottom is in compression. So with these sign conventions of, our shear making the element want to spin clockwise is positive, and then for the bending moment, always making sure that we plot the bending moment on the tension side, then the positive negative stuff will sort of work its way out as we do our plotting. So now that we have that, we can finally get back to sort of the task at hand, which is finding the shear and bending moment diagrams for this beam. And so if we just sort of bring this back here, what we'll do is we'll start with the free body diagram here, just because we can then look at the relationship between the loading and the shear and bending moment diagrams, which we will plot up. WL over 2, WL over 2, and at a distance L. So the first one we're going to plot is the shear force diagram, V, and we'll just even put our little sign convention next to it. So we will put that a line here for plotting that one. And so what do we have? Well, we have an equation for what our shear force should be. It's this WL over 2 minus WX. So what we can do is, we can plug in various values of X, and we can find out what's that going to be. So I'll write that over here. So if we have V equals WL over 2 minus WX, well, first place to go is to start with the our boundary conditions, when X equals 0 and when X equals L. So we'll even just do this. We'll say X goes in this direction. So at X equals 0, that turns to 0. So V equals WL over 2. And at X equals L, this is WL, so you have WL over 2 minus WL. We get minus WL over 2. V equals minus WL over 2. Well, we can go ahead and plot those values up. So at X equals 0 and at X equals L, we know we have WL over 2, WL over 2. And we can see from this equation where we will start, and this is just simply a linear equation. This is just the slope of the line. So as X progresses, it will slowly deteriorate at a constant rate of W times X. And so what we know, if this is a straight line, well, we're going to start here and going to end there. So we can just go ahead and connect the two locations. And what we want to know is we want to find out, well, what's the location at which it equals 0. So I'll on my shear force diagram, I'll even put the sign convention so we know what's positive and what is negative. And so V equals 0, so this point right here, well, we can just set this equation equal to 0. So we have 0 equals WL over 2 minus W times X. So we get W times X equals W L over 2. And then we can divide out. We get X equals L over 2. So we know that V is going to be 0 at X equals L over 2. Very good. So now what we'll do is I'll just transfer some of these points further down, and you'll see why in a moment. But it will make some of the relationships that we're going to have become a bit more clear. So if we draw there, and this is for our moment. And again, we're going to say the positive moment is compression on the top. This beam is bending this way, so the tension side is on the bottom. So we're going to plot the moment on the bottom. So our moment equation, we have m equals minus wx squared over 2 plus wl times x over 2. And again, that's just coming straight out of our free body diagram. So what we want to know is that, what are our points here? Well, we know that at x equals 0, the moment equals 0. That makes sense. We just replace 0 for x, so 0 times anything is going to be 0 plus 0 times anything is going to be 0. So we know that the point starts at 0 here at x equals L. We can also plug in, so we would have w minus w times L squared over 2 plus w times L, so that's L squared over 2. Well, that will simply go to 0. So we know we have another point at 0. And again, this is one of those good times to stop and consider, does this make sense? And it should, because we have a simply supported structure where the ends are a pin and a roller. So we can't sustain, we can't resist any moment there. So the moment should be 0 at a pin. And it's the same if we have a hinge. So, and then we know that this is a parabolic relationship. So we will have a moment diagram that will, apologize for the, I'll try to draw that a little bit better. There we go. We'll draw something like that, where this is a parabolic curve. How do I know it's a parabolic curve? Because this is a parabolic equation where it's an x squared. But what we want to know is, what is the max moment? So, what we can do is we can just plug in values of x from 0 to L and slowly plot this up. If we're doing that by hand, that's very, very tedious. If we are doing it with a computer, it'll work. But we want, say, a quick way to identify, well, what is the maximum moment. So what we'll do is we'll recall that the shear force is just the change of moment over distance. So that's just change of moment over change of distance. So we'll define this a bit more formally here in a moment, but for just now, I'll have you take my word on that. And so, well, what is this? Well, this just means that the shear force is the derivative of the moment diagram. And so, we can prove this to ourselves, where if we just take dm dx equal to minus w x squared over 2 plus wl x over 2, take that derivative, what we'll find is we get equals minus 2wx over 2, those two cancel out, plus wl over 2, and then we get dm over dx equals wl over 2 minus wx, which equals v. So all of this should make sense, and that's always good when our forces actually meet the definitions. So if we know that the shear force is just going to be the derivative of the moment over a small distance, we know from calculus a function is at its maximum when its derivative think of this as the slope equals 0. So all we need to do is find out, well, when does the shear force equal 0? Well, we've just done that up here. V equals 0 at x equals L over 2. So we know that the slope of the moment diagram will be 0 at x over 2. So we've got dm over dx equals v equals 0 at L over 2. So in order to find the maximum moment, all we have to do is plug in L over 2 for x for our moment equation up here. So let's do that real quick. So we'd have max moment equals minus WL over 2, all of that squared, over 2 plus WL times L over 2 over 2. And again, all we're doing here is just plugging in L over 2 for x in this equation up here. So let's go ahead and solve that. So let's pull out this 1/2, and we would get minus WL squared over 4 plus WL squared over 2, and that will give us 1/2 times minus WL squared over 4 plus 2 WL squared over 4. Simplifying all of that down, we get M max equals WL squared over 8. So that's actually that's all we need to know, and then we can plug this value into M max equals WL squared over 8. So we'll take just a brief point, and let's have a look at this plotted up. So what I've done is I've gone through in Excel, and I've taken these equations. So you can see this is the same equations I have plot that we've just derived, and then I've plotted up for the loading diagram, the shear force diagram, and the bending moment diagram. You can see that yes, indeed, the maximum bending moment occurs where we have 0 shear, as we would expect. So that's It's always good to see when that comes out. And, this is where these equations can be quite useful, is if we want to do these things like, try to plot these up in a computer, or the like. Computer needs these equations in order to function. However, for us, that took a while. And granted, I spent some time explaining it, but overall, shear and bending moment diagrams are a very useful tool for structural engineers, and it's something we want to be able to generate very quickly. So if we're going to do that, we need to have some tools to get there, such that we don't have to go through and brute force and do a free body diagram every time. Knowing that we always can is important, and it means that if we're ever stuck, we can use free body diagrams to kind of get us out of that jam. But let's see, is there anything that we have about these shear and bending moment diagrams and some of the relationships that we might have seen here, from where we had sort of constant load, linear, shear, parabolic moment that we might be able to exploit. So in order to investigate that, let's have a look at a general case. So you see I've got a simply supported beam with some arbitrary loading on it. And so what we're going to do is we're going to draw the darn free body diagram. So I'm going to make a cut. I'll have one end labeled A, one end labeled B, and this cut, I'm going to make it a value dx long. So all that means is that it's an infinitesimally small section of this structural element, so this beam in this case. So if we do the free body diagram, and I'll draw it nice and large so we can see it. So it has some, over this very, very small distance, we can approximate the load as linear. And that's, that's a pretty common approximation for calculus, that as we get smaller and smaller and smaller, a line will, a linear change will make sense. So we'll assume that it's constant over this very, very small distance, d sub x, and we'll call this end A and this end B. It has a shear force on both sides, and it has a moment on both sides. And the shear force, and so it's got this value W here. We have the shear force V and the bending moment M. Here, this shear force on this side is V plus dV, because we've moved some small distance, so the shear force will be slightly different. Same with the moment here, we have M plus dm. So let's solve the statics and see if we can find these relationships between our load, our shear force, and our bending moment diagram, and then we can see if we can exploit those relationships so that we can draw these shear and bending moment diagrams quickly. So starting with sum of the forces in the y equals 0. So we have minus W times dx plus V minus V minus dV, and all of that equals 0. So the two V's cancel out, and then all we get is we can send this dV over and divide by dx, and then we get W equals minus dV over dx. And what does this tell you? Well, this means, we now have a relationship between our load and the derivative of the shear. So the applied load is going to be equal to the change in shear per unit length And you're thinking about that. Another way is the slope of the shear force diagram equals the negative of the magnitude of the load. And we saw that in the example we just drew up, where we had a constant shear force, and then we saw that our shear force diagram just sloped down at a constant rate. So let's have a look at the moments here. So if we go sum of the moments at A equals to 0, well, we've got negative m minus w times dx times dx over 2. Then we have minus v plus dv, all of that times dx, plus m plus dm equals 0. So the moments cancel out. Let's do a little bit of a simplification. W times dx over 2 minus v times dx plus, it's going to be plus a negative dv times dx plus dm equals 0. Now remember, dx is a really small number, and so dx times itself is going to be an even smaller number, which means that's going to approach 0. So dx times dx is approximately 0, which should make sense. And a small number times another really small number will be an even smaller number squared. Same thing with, dv is a very small change, because we've only gone a very small distance, and we know that our shear is tied to our unit load, and our applied load hasn't changed that much. So we can also make a pretty comfortable assumption that dv times dx is approximately 0. Well, that means that this will go to 0, and this one will also go to 0. So what we're left with is minus v over dx plus dm. And that all simplifies down to v equals dm over dx, which we showed earlier in the lecture. And we proved this. The derivative of the moment is our shear force. And so what does that mean? It means that shear equals the change in moment per unit length. And it's these relationships here which not only will help us draw these shear and bending moment diagrams, but also as we progress through this class, will give some insight into our ability to, solve some of these more and understand the derivations of these mechanics properties. So we'll just do some rules for relationships. So these are for shear, magnitude of the load equals the negative slope of the shear force diagram. And then for moment, the magnitude of the shear is the slope of the bending moment diagram. Moment is max or minimum. Both are true. When v equals 0. And again, that's because the slope is 0. So by max or minimum, I'm talking sort of in terms of when the curve has a slope of 0. And then the final bit is that integrating v gives the value of moment. So let's have a look at some of that for some graphic examples. So first one we've already had out here, where we have a uniformly distributed load, linear shear force. So we've got load is constant, shear is linear with constant slope. And V equals the reaction. V equals the reaction. And so again, you've got V, and then when V equals 0 is just going to be the reaction divided by the slope, and that equals WL over 2 divided by W equals L over 2. And we've shown that quite clearly in the example where we worked through it with free body diagrams. We know that the maximum moment occurs when the slope equals 0. Slope equals 0, which is when the value of the diagram is 0 here. And then if we want to find out what the value of M max equals, as I said, it's going to be integrating the shear force diagram, and integrating is essentially the same as taking the area of the V diagram from a boundary condition that we know. So essentially what that's going to be is we're going to take this area right here, where we go from 0 to our point of interest. And so we know what our boundary conditions are. We can take that area, and we know that this area is going to be equal to that value just from our rules from calculus. So that area is going to be WL over 2, which is equals WL over 2, WL over 2, just that reaction there, times L over 2 times 1/2 because it's a triangle, and we get WL squared over 8, which is exactly what we got when we derived it using free body diagrams. So just right here. So, and then, just going through these next two examples just quickly, just for the sake of time. If we have a point load, well, we have no applied force here, so our slope of our shear force is constant. It's 0. Then when we have a discontinuity, well, we're going to jump up, and then we have no shear force here again. So again, we're going to have force values of P over 2, and this is a good point. We must have our shear force and bending moment diagrams close in order to have everything be in equilibrium. Then for our moment diagram, here, so again, it's a happy beam. It's plotted on the tension side. To find out what this value is, so we know that it occurs at L over 2 because that's when our shear force equals 0. So we can simply take this area, which is going to be P over 2 times L over 2, and we get P L over 4 is our maximum moment. And then finally, we have a triangular load. I've got it here on a cantilever, but this is really to show you that we'll go from a linear force distribution, and then so this is, think about this as like x to the 1 to a parabolic, so you've got x to the 2 to a cubic, x to the 3 for the different distributions that we have there. And then, as I said before, just note that all your shear and bending moment diagrams must close in order for this to be in equilibrium. And you can use that similarly to the way we use a statics check, in which if your shear and bending moment diagrams don't close, then you know that you've made a mistake somewhere. So I hope you found that helpful as a refresher. What we'll do in the next video is we'll start looking at some more complicated structures. We'll be looking at frames, and we'll be using a combination of these graphical methods as well as free body diagrams, and I'll just kind of show you how you can mix and match them so that you can do these efficiently and effectively. So with that, thank you for watching.